Good morning, afternoon and evening to our audience today. Welcome to the latest webinar hosted by Device Authority. My name is Rosa Lenders and I am very pleased to welcome our key speakers for today, Brian Whittin and John Penny. Brian is Senior Director of Internet of Things at Symantec. For more than 20 years, he has built security into countless things, including aircraft, spacecraft, industrial control systems, consumer electronics, critical infrastructure and more, which are used in banks, retailers, hospitals and manufacturing companies around the world. At Symantec, Brian's work has directly contributed to embedding security into over 1 billion IoT devices. John is the co-founder and Chief Security Officer at Device Authority. He is passionate about data security and plays a particularly active role in driving initiatives to protect the privacy and integrity of information traveling across ecosystems making up the Internet of Things. We expect the webinar to last approximately an hour, and you will be able to submit questions via the chat window. At the end of the webinar, we will then respond to the questions that have been submitted. Contact details are included in the final slide, so if we are unable to cover your question today, or should a question arise afterwards, please contact us. A recording of the webinar will be made available later this week on the Device Authority website, and everyone who registered will be emailed the link. I shall now hand over to Brian.
Thank you. I hope everybody's able to see my slides in blue. Rosa, can you confirm?
Yes, we can see them, Brian.
Perfect. So over the last few years, we've helped build security into over 1 billion things, doing that working with over 100 partners such as Device Authority. And we've been doing this across several verticals because of the many, many different ways that the Internet of Things can change our lives, from connected cars that stream navigation data that help us avoid traffic, easing our commute home, and medical devices better connecting doctors and patients to improve lives and outcomes, as well as big industrial systems around anything from jet fuel, where changes as small as 1% produce billions of dollars of savings, to the manufacturing systems that produce tens of millions of cars per year. Now, many companies question whether or not the projections of billions and billions of smart connected devices will really materialize. But the reality is that the semiconductor industry is already generating 20 billion microcontrollers per year that are going into smart products worldwide. Over 5 billion of those are connected today. And the projections for 2020 are really just a reflection of how many more of them are going to become connected. And it's that connectivity that has the ability to change our lives for the better in so many ways, but it's also that connectivity that is an avenue of attack. So this, believe it or not, is not doom and gloom prediction, but rather a quick history of things that have already happened, including a 3-kiloton pipeline explosion in a fortunately uninhabited area when maliciously tampered firmware in oil pumps accelerated oil past safe limits, and of course the friction of the oil on the shell of the pipeline caused it to overheat and explode. December, just over a year ago, a steel mill had something so substantial as a blast furnace damaged through cyber attack that came in initially through the IT side of the network and then through a gateway separating the operational plant floor network from the IT network. I think many of us saw the power outages in the Ukraine with a couple 100,000 people without power, and hundreds of critical infrastructure sites have been hacked in North America with dozens compromised to root levels. June of last year, it was disclosed 3 hospitals were breached via MRI machines, X-ray machines, and blood gas analyzers. Machines that we don't normally consider vulnerable, and yet they're so vulnerable, they're a liability to the rest of the network. I think many of us saw the video of cars remotely hacked and remotely crashed. At the same time, in the real world, not just proof of concept, but at scale, large numbers of cars are being stolen through security vulnerabilities in keyless entry and keyless ignition systems, stolen right out of the owner's driveways and loaded onto container trucks in the morning before the, not container trucks, but container ships in port to be shipped out of the country before the owner even wakes up in the morning. So in that context, to do better with security for these smart connected products, we need to understand sort of what's fundamentally different about them compared to information technology. Well, in the personal computing desktop data center era, security was sort of most easily delivered, by disk. You could buy hardware anywhere you wanted and just add your security of choice, either antivirus or host-based intrusion prevention, by just downloading the software or slipping a disk in it to bolt on security to nearly any hardware long after you'd bought the hardware. In contrast, you can't really slip a disk into your thermostat. You can't slip a disk into your industrial robot. And you can't slip a disk into your pacemaker to add security software, even if you wanted to. Even if you could overcome the technical countermeasures against modifications, many of these devices have warranty and support clauses where the maker of the device won't support it, won't stand behind it if you're tampering with it. Now, avoiding those warranty and support clauses might be an option for a hacker who wants to play around and have fun on their smartwatch, or maybe even their thermostat, or sometimes even a car. But it's really not an option for industrial robotics and MRI machines and other equipment that cost hundreds of thousands or even millions of dollars. And so for those reasons, security often has to be built into these new smart connected things, built in by design. And there are many challenges in doing that in the Internet of Things that we didn't face, that nobody faced in the desktop data center era. And the biggest, perhaps, is fragmentation. I'll speak to limited computing resources in a minute because that turns out to be a tractable challenge. In my mind, the bigger challenge is the fragmentation because the hardware architectures, range across a much broader range of not just 32-bit and 64-bit, but rather 8-bit, 16-bit, and countless architecture, AVR, MIPS, RISC, in addition to x86 ARM. And then the operating systems are even more fragmented, heavily fragmented by vertical. In some verticals, the leading vendor of operating systems has a 6% market share. So it's no longer the case that you can build for one hardware software stack and cover 80 or 90% of the market. You have to literally, in some cases, support a dozen operating systems to cover 80% of the market. And the protocols are even more fragmented, in some cases with thousands of protocols, hundreds in each vertical. So in that context, what we wanted to do to help build security into all of these different things is sort of step back and realize that no one company can do it all. It really takes an ecosystem to build security into all of these things, and it has to be done working with partners. So we've worked with many of those partners to define a vendor-neutral security reference architecture for what it really means to protect systems from end to end, from the lowest layers of the silicon to the loftiest layers of the cloud, protecting every potential weakest link in between. Because anything that you leave unprotected will become the Achilles heel that those smart, sophisticated attackers will seek out and use against you. So working with partners, we've defined this reference architecture really as 4 cornerstones. I mean, the IoT architecture itself is pretty commonly understood as devices and sensors and actuators at the lowest layer, talking to and sometimes controlled by servers, either running in the cloud or in an on-premise data center. And that communication often, not always, but often goes through a gateway. And so the cornerstones then start with protecting the communications between the devices, and then really protecting each device well individually, and then managing large numbers of devices over time, because security is never done, and any device where you get it wrong or where it gets misconfigured over time, it becomes an Achilles heel that an adversary will exploit. And then no matter how well you do each of those first 3 cornerstones, you need a security analytics capability to really keep an eye on the whole system and find and fight the adversaries that are sophisticated enough to walk through extremely well locked down environments, leaving just footprints in the sand without tripping any alarms. So those then are the 4 cornerstones, and I'll spend just roughly a slide on each of these. And I'm very glad to have John on the line from Device Authority to double-click really on what it means to protect the communications, because we depend heavily on partners like Device Authority for getting that part right. So the first, for protecting the communications, a lot of people don't believe that these extremely constrained computing devices can do powerful security. And that's really a shame, because they can, even if most engineers don't yet know how to do so. And that's really because most security engineers haven't had to work in these extremely constrained computing environments, and most of the engineers who do such great work in extremely constrained devices, you haven't really had to do security at this level. So I want to walk through an example of, surprisingly, how really serious security, in this case, elliptic curve with a 256-bit key strength, which is good enough for U.S. national security secret-grade information, can be built into even devices with 30-year-old architectures. So this 8-bit, 8 megahertz chip with just 2K of static RAM has roughly the computing power of the chips that were, really emerging in the early 1980s. And this chip can do that kind of elliptic curve, 256-bit key strength, crypto on the hour, every hour, signing something or verifying a signature, on the hour, every hour for 20 years, and only use a slice of a AA battery. Of course, at 8 megahertz, it's going to take 25 seconds to do it, but if your use case is a pipeline where you have unattended sensors that literally need to last decades, and you're only signing data once an hour to transmit that telemetry of how that section of the pipeline is doing, the 25 seconds isn't a showstopper. But for a lot of other use cases, things need to work a lot faster. So if you need it to work faster, just buy a faster chip. 10 years ago, roughly 10 years ago, the 16-bit chips eclipsed the 8-bit chips in volume. And these chips are really only 25 cents each. And they can do the same crypto also on the hour, every hour for 20 years, only using a slice of a AA battery. And they can do the same crypto in roughly 3 seconds. Now, a lot of really good engineers would look at this and they would say that OpenSSL and the other crypto libraries which they're familiar with could never run in just 2K or 10K of static RAM. And that's true for the libraries that they know, but that's why other cryptographic libraries, such as open source implementations, like the Nano implementation of elliptic curve that can run in less than 2K of static RAM, or the micro implementation of elliptic curve that can run in less than 10K of static RAM, are so important. So crypto can run in these extremely constrained devices. You just have to know how to do it. And part of that is starting with the right libraries. But the other thing that's really crucial is getting the key management right. And that's where Symantec, as a certificate authority, having embedded security into over 1 billion devices, and partners like Device Authority can really help get the key management right at scale and really simplify it for you as a customer to make it much easier. Of course, for a lot of use cases, even 3 seconds is slow. Fortunately, the newer 32-bit chips can do the same crypto in the millisecond range. 32-bit chips, many of these are 50 cents each. Some of them are the physical size of a human hair, and they can do this crypto just on the energy harvested from things like bridge vibration while salted into the concrete of a bridge. And so given that you can do such powerful crypto with things so physically small as a human hair, with such little battery power as the energy harvested from bridge vibration, and costs as low as 50 cents each, I don't see how cost, physical size, or battery budget are any longer an excuse for not building in serious security into these extremely constrained devices. And of course, if you can build in serious security into these devices, if you can build in strong crypto, you can use that crypto to both authenticate communications between the devices, and you can also use it to cryptographically control what code is allowed to run on the device through things like secure boot and code signing to verify that the code running on the device is really your code as the maker or owner of the device and not some attacker's code. Of course, protecting these devices is more than secure boot and more than code signing. After the right code is loaded and running, you want to make sure that it stays running, and that's where you need runtime security. And the good news is that today we have a lot better options than the old school, old world, signature-based, blacklist-based, update required, traditional approaches to antivirus and anti-malware. Today's embedded security technologies, like Symantec Embedded Security Critical System Protection, use whitelisting and behavioral and policy-based approaches to really lock down the system so that it can only do what it was designed to do. And if somebody tries to force it to do something else, that change in behavior is immediately detected and shut down. And that's how we block even zero-day threats, previously unseen threats. That's how we proactively block all kinds of threats that we nor anyone else have ever seen before. And the good news is that these whitelist and behavioral solutions can run in extremely limited resources, often just a few % of the resources available even on credit card-sized single board computers and other embedded systems. And so with extremely limited resource protecting against seriously sophisticated attacks, that's the second cornerstone of not just protecting the communications, but protecting the devices individually. The next step, of course, is to manage those devices over time, especially because you often have so many of the devices to manage. Now, a lot of companies look at the challenge of embedding update capabilities into these devices, and they try to avoid it because it's so difficult to update so many of these devices. In industrial control settings, for instance, you might only get an annual or a quarterly maintenance window. But given these devices are in the field on average of 19 years, an annual update cycle is 19 times better than no update cycle. For medical devices like MRI machines and X-ray machines, they'll often be in the field 8 or 10 years. Cars, on average, are on the road 11.9 years. And so, given that the threats are continuing to evolve so quickly, that over-the-air update capability needs to be built into the devices ahead of time, so that no matter what the future holds, you're ready to adapt to it. Because if you're not nimble, I guarantee that the adversary is. And given that for many of these operating systems, not just Linux, many of the operating systems, vulnerabilities are discovered on a daily basis, you really need that over-the-air update capability built in from the start. Now, for some of the proprietary operating systems, they pride themselves in having had fewer vulnerabilities publicly discovered, but our experience has been just because they come to light less quickly publicly, that doesn't mean that they haven't been discovered behind the scenes and quietly exploited by attackers who just didn't disclose the vulnerability in some of those proprietary operating systems. Of course, there are a lot of other reasons that companies don't build in over-the-air updates. Many of them fear that updates are going to kill battery or kill bandwidth. And that's certainly true if you take a monolithic approach to updating gigabyte-sized images. In contrast, if you take a very granular, a surgical approach to doing your updates, where you update just effectively a few lines of code or a 40K block size out of that gigabyte-sized image, you can literally do hundreds or thousands of updates consuming less battery and consuming less bandwidth than a monolithic update. So granularity of these updates is crucial to getting over-the-air updates to scale. And for that granularity to work, you have to have a software inventory management system that supports the granularity, as well as a code signing architecture that supports the granularity. Of course, if you build a good over-the-air update system once, either for security updates or for normal functional updates, you can use it for either. Build a good over-the-air update infrastructure once and use it for both security and functional updates. Use it to pull back your security telemetry and your normal telemetry for both security control, normal control. And you can also then use that infrastructure to push out new functionality and new features and innovate faster for your customers, delivering new value to them faster than if you waited for them to buy new hardware. That's a great way to not only improve their perception of your product, but continue monetizing products by delivering value to your customers long after you deliver the hardware to your customers. And again, I mentioned earlier, no matter how well you do the first three cornerstones, protecting the communications, protecting the devices, and managing the devices over time, you need a security analytics capability to find and fight those seriously sophisticated adversaries that can walk through such a locked down environment, leaving only footprints in the sand, not tripping any alarms. And detecting such threats really requires a strong understanding of how your system should be behaving. Fortunately, the machine learning for modeling how your system is behaving when it's not under attack, companies like us have mastered that machine learning from doing security analytics on trillions of security events annually and distilled that into a form that can be embedded even in compact embedded systems that can run in a small slice of an engine module on a car, such as the anomaly detection for automotive product that is coming to market so quickly. And with that machine learning, it's the same machine learning that we've already used to detect some of the most sophisticated threats in other verticals. And with that, I'll just recap on the 4 cornerstones: protecting the communications, protecting the device, managing the devices, and then the security analytics to detect those seriously sophisticated adversaries. Our products in this context really are the device certificates and the roots of trust, both of which we work with Device Authority, and I'm very glad that John's going to be giving so much more detail there. And then for protecting the device, I mentioned the code signing, both the certificates and the cloud-based services for helping with code signing to cryptographically control the code running on the device to make sure it's your code, not some attacker's code. And then the runtime security from embedded security, critical system protection. For managing devices in different verticals, we have Control Compliance Suite and the Altiris portfolio. And then for security analytics, we have both the embedded anomaly detection for automotive and an anomaly detection capability for industrial control systems coming soon, as well as global analytics, managed security services for helping take that security telemetry from so many devices and really help you analyze it on the back end. But with that, I'm happy to hand over to, before I hand over to John, just one quick note. A lot of companies come to us saying that this is great if you make the IoT things that you're trying to sell. But what if you're a factory or a hospital that buys a lot of these smart connected products from suppliers? Many of them are very frustrated with the garbage level of security, and they call it the garbage level of security that they've been getting from their suppliers. But then when we ask them, if you're not happy with the level of security that you're getting, how did you specify in your requirements to your suppliers what you wanted for security? What were the requirements that you specified? Because that's where buyers have a lot more leverage in many cases than they realize. And by specifying smart requirements around code signing, around authentication, and around runtime security, and around over-the-air management, buyers can really get from suppliers the types and levels of security that they really need. And we've seen that proven true in vertical after vertical. So happy to take more questions on this later after John's talk, but right now I'd really like to hand it off to John for him to double-click on what it means to build in effective security into these devices, especially around the authentication. So John, over to you.
Thanks very much, Brian. That's great. Some fabulous insight into some of the challenges that exist there, and some great recommendations and thinking on how to address those. So thanks for your input. Good afternoon or good morning, everybody, depending on where you are in the time zone. My name is John Penny. I'm the CSO and co-founder of Device Authority. I'm going to be covering off really 3 key areas in my session in the next 15 to 20 minutes. I will spend just a brief amount of time providing with an introduction to Device Authority. There have been some changes in our organization over the last few weeks. I do see some familiar names on our attendee list, so welcome back to those, but I know there are quite a few new attendees as well, so I'd like you to get an understanding of who we are and our pedigree and where we've come from. I'm going to be moving on to provide some insight into the challenges around credential provisioning at IoT scale, and how basically Device Authority and Symantec are helping customers solve these problems with automation in these key areas. So very quickly on some history of Device Authority. As I mentioned, we've had some pretty significant changes over the last few weeks where some of you may know we were, before those changes, known as Cryptosoft Limited. We actually were formed in around 2010 where we built our security platform to specifically secure M2M or application-to-application data flows within the traditional enterprise data center space. And in fact, over a number of years, we have acquired a number of fairly substantial customers who have adopted our technologies to provide the security plumbing for some pretty significant and critical applications within those enterprises, and also extending out to supply chains. What we saw in that time was some significant opportunity for us to apply some of the lessons that we'd learned in the enterprise and really leverage the proven technology that we developed in that time to address some of the challenges that existed specifically within IoT. So in 2014 we secured some funding from our VC partner, Turn PLC, and spun out a specific completely dedicated IoT security business to address that market. So we launched that really in Q1 2015, again specifically taking our existing platform and applying it to IoT security, and addressing what we saw as some of the significant challenges really, specifically in terms of securing data payloads within IoT data flows. We formed actually a strategic partnership with Device Authority not so long ago, as you can see there, Q3 2015, and that was really to help both increase the efficiency of existing certificate deployments and provide some automation around those and provide more security around those, but also to deliver those at IoT scale. We also have a significant, it's worth mentioning, strategic partnership with PTC ThingWorx, one of the leading IoT platform enablement organizations, where we've developed a security extension for their IoT application development platform, allowing their customers to very quickly and easily add Device Authority type security services into their application development processes, and also obviously get the benefit of the Symantec scalable PKI at the back end. That integration with Symantec was launched in Q1 actually this year, where we're enhancing their Internet of Things Roots of Trust program to extend capabilities to data payload encryption and also provide automation security services around device onboarding and certificate provisioning, which I'm going to come on to talk about in a moment. And so the significant event for us really was in 2016, in fact just some 5-6 weeks ago, we actually merged with the Device Authority. There were so many similarities and benefits in terms of the two businesses working together that we decided to merge, and we assumed their name, which is how we've come to be known as Device Authority now as a combined business. Significantly, in terms of accolades, actually Device Authority in 2015 were awarded the Gartner Cool Vendor Award for their technology innovation, and then in fact just as we were completing the merger, in fact we heard that Gartner had awarded us as Cryptosoft the Cool Vendor Award as well. So I think we're the first sort of combined operation to receive that award 2 years running in 2015 and 2016. So a quick introduction to what it is we actually do. As our strapline states, we're simplifying security for customers in the Internet of Things by delivering a strong trust anchor for the identity of things. And I'll talk about what that is in a bit more detail in the slides to come. We're leveraging that trust anchor and the keys that we're able to derive from that to provide data-centric encryption services for all IoT data. So this is really layering on top of existing provisions that might exist in the IoT around transport-based security, which I think for anybody that's looked at trying to achieve end-to-end security using transport security alone, particularly in the complex data journey that IoT data is subjected to, is very challenging. So we're really layering on top of that to provide specific security around the data payloads themselves. We're driving all of that through business policies. So in a complex environment such as IoT, which is really about complexity as much as it is about scale, and we obviously always hear about the volumes of devices, but it's as much about, I think, the complexity of those interconnections that really require us to take as much as possible a hands-off or a hands-free approach to driving compliance within that end-to-end environment. So business policies are absolutely critical to driving integrity and trust. And in terms of where we're applying those technologies Some of the key innovation areas for us and some of the key areas where we're working with customers is around service access control. So that's really leveraging our trust anchor to deliver authentication services, but also the certificate technologies from Symantec to deliver that, but not only around devices, but also around the service stack that sits above those devices, such as applications and APIs, etc. Data asset protection, which is really about the data-centric encryption services and protecting valuable IP assets or regulated data moving across those ecosystems. And critically within IoT, as Brian has already mentioned, secure over the air or over the network is absolutely critical in terms of providing a simple method and secure method of delivering over the air updates at the frequency that is demanded by IoT implementations. Revenue stream protection is another key area for us. And finally, secure certificate management provisioning, which is really the essence of our strategic relationship and alliance with Symantec. So, in terms of why some of these challenges are particularly significant in IoT, I think we need to look at some of the economics and complexity of IoT to understand that really what that results in is this massively expanded attack surface. According to Gartner, sorry, not according to Gartner, but if you consider some of the following elements in terms of a typical IoT infrastructure, we quite often see platform as a service and infrastructure as a service being fundamental to building out that sort of economical IoT infrastructure. These aren't things or elements within the end-to-end system that you can build yourselves in-house. Public networks obviously form a critical part of these, particularly cellular networks, and connected all these together with these complex supply chains, which are really becoming the new reality in IoT. And I think interestingly, we're seeing in the emergence of edge analytics or fog computing a process whereby we're distilling a lot of the valuable data out from the less valuable data at the network edge. We're really doing, a significant element of the job on behalf, for the bad guys, given that actually what results in us sending out across these potentially untrusted networks in that end-to-end journey is a pure distillation of that valuable data that may be of interest to a malicious third party. And lack of standards, I think, is a key one. I guess anybody that's looked at this in any detail, can see that although we do have some standards emerging, both in terms of things like secure elements within hardware and within communications protocols, I think again, as Brian pointed out in his presentation, it really is quite complex right now, and there are many standards to choose from. So it's really just too hard to pull something like this together. Given that landscape. And all of this really adds up to these multiple off-ramps into untrusted networks and the challenges that that's presenting to traditional transport-based security models. So as I started to mention and went off in the wrong direction on that previous slide, so Gartner predicts in a recent report called Gartner Predicts 2016, Security for the Internet of Things, that there are some significant challenges ahead, and I think I've pulled out really 2 or 3 significant ones here that I think are relevant to this conversation. Firstly, by 2018, that over half of all IoT device manufacturers will be unable or challenged in addressing product threats emanating from weak authentication practices. And surprisingly, today we still see examples of hard-coded credentials in terms of default usernames and passwords as the sole means for accessing devices, and clearly that represents a pretty significant attack surface for those devices. Interestingly, by 2020, they're also forecasting that a quarter of all identified attacks in the enterprise will involve IoT in some shape or form. But then we have this misalignment on IoT security budget allocation, with only 10% or less than 10% of IoT of security budgets allocated to IoT. So there's certainly, I think, a balance to redress there, and that's kind of food for thought. But actually, in terms of what we're doing, Device Authority in conjunction with Symantec are delivering a lot of the capability here. It's really discovery, provisioning, authentication, data protection that's going to account for the bulk of security spend, even within that 10%. So, and once again, I think to build on Brian's part of the presentation, which very eloquently described a number of breaches that we've already seen within IoT. A fairly simple Google search, I think, that I undertook, uncovered approximately a decade of IoT-related breaches, and that started really, I think, with Stuxnet, which I think we're all pretty familiar with, famously orchestrated by the US and Israel. At the end of the day, these were industrial control systems. So these were traditional SCADA-based systems that were breached. We have many reports fairly recently from the United States Department of Energy disclosing over 159 successful intrusions over a 4-year period, including 59 root compromises. So gaining CPU privileges, and no real heads up on what came about as a result there, but obviously those are pretty serious incidences. Smart grid breaches through building management software, a pretty good example of an IoT-related breach. Chris Roberts famously now, I think, through an in-flight entertainment system, 15 to 20 times over a period of 3 years. Famously arrested for that, even though I think we did deliver a pretty good service in highlighting some of the challenges that exist there in terms of weaknesses within those systems. An oil rig breach, I think a good example again of a critical control system that was penetrated off the coast of Africa. 19 days that took to get that operational again. And if you think about that in the context of the movement of global goods around the world, with 90% going via our oceans, that's has pretty serious implications. And finally, I think one that Brian may have already mentioned in his slide, very recent, but worth reading up on if you haven't come across this one, as it was really the first significant hack to take down a complete power grid in the Ukraine, affecting millions of customers for a number of days. And again, that was really just done through some simple breach of VPN credentials, I think on some home working machines to gain ultimately direct access to that SCADA network. So really in IoT, I guess what we need to be thinking about is a new paradigm, and I think that new paradigm really is about enablement rather than development. If we think about the time to value curve that exists in IoT, we can't realistically be thinking about traditional approaches where IoT application development is measured in months and years and has an associated high cost sitting in the top right of this curve. And then, of course, to add in all of the relevant security components and in-house key management infrastructures to support that, further adds to that time frame and cost equation. So the new paradigm really, and the IoT necessity, is really all about time to value measured in days and weeks, and certainly companies like ThingWorx are delivering this for customers around their enablement of IoT application creation, and again measured in days and weeks with very low cost compared to those traditional approaches. And in terms of creating secure IoT application enablement with device authority and the Symantec managed PKI elements at the back end, we're really introducing this concept of security enablement within these IoT application environments. So to move on and talk just briefly about some of the challenges that we see within the IoT in terms of certificate provisioning and device onboarding, let's consider some of the following elements. It's a fairly well-known fact that the cost of managing a single certificate in the wild is in the region of around 4 hours per annum. That's per single certificate. So I think if you look at the average lifespan of an IoT device, and I think Brian covered this very eloquently, is somewhere in the region of 10 to 15, or maybe even arguably 10 to 20 years. It doesn't take a mathematician to work out that those costs of management in terms of certificates in the wild can soon grow to pretty astronomical figures in the context of IoT. And those are growing. So I think the longevity of an IoT device is pretty much the the bedrock of IoT's value proposition. It's absolutely critical that organisations get the greatest amount of value over an extended lifespan of an IoT device. So that really presents further challenges in terms of certificates that we need to both provision and manage within those extended longevity environments. I've talked about standards already, and certainly, particularly in legacy devices, we see, quite a prevalence of lack of supporting secure elements or TPMs. So being able to provide security around traditional certificates in those kinds of situations is pretty critical and quite challenging. And of course, in terms of those extended IoT device lifespans, revocation and certificate reprovisioning windows are shrinking. I mean, if we need to, for example, revoke a certificate across maybe tens, if not hundreds of thousands of devices, and we need to do that on an increasingly frequent basis, then we need a particularly strong platform to help manage that and do that in a zero-day fashion across all devices if possible. We've already talked about OTA, and again, Brian mentioned the increasing frequency of the requirement for patching and the requirement for that to be over the air. So I think that taken into consideration, really certificate automation and the security around those certificates is really not a nice to have. It's pretty much a prerequisite for the Internet of Things. So if we think about some of the elements, therefore, that we need to see within a certificate automation and security platform, an IoT-specific solution really should be able to provide some form of device-bound secure enrollment of certificate. So we are able to move away from this loosely coupled relationship of a certificate being provisioned onto a device, but that we create an actual binding using some of the hardware properties of the device itself, wherever possible, to create that trust anchor. We should also allow for a hardware agnostic approach to our customers, so that we can use a single process across the entire IoT domain for onboarding and ongoing management. And I think, as I've already referenced previously, as much as possible, this should be a hands-free, policy-driven approach to the automation of certificate lifecycle management. Where we don't have secure hardware elements, of course, then we need to offer strong security for local certificate storage using strong and trusted encryption methods, and offer and deliver this zero-day revocation and reprovisioning at IoT scale. Wherever possible, we should be able to leverage these underpinnings for file-level encryption for IoT payloads, not just actually, I should say, in transit, but also in storage. And finally, as a reference point back to the fog-based computing models, it's going to become increasingly critical to be able to support efficient distributed secure OTA updates. So that would be the send once, update many, particularly where we have downstream lightweight constrained devices where maybe a gateway is responsible for applying those updates or those certificates. So in terms of some of the specific elements the device authority is helping address there in conjunction with Symantec, we need to look at some of the factors that really present some challenges, and from top to bottom in terms of these four areas. We have, and I've already mentioned this, the fact that really traditional certificates, where they're provisioned in the traditional fashion, don't really identify devices specifically, because it's really a loosely coupled relationship, given that we've manually provisioned that onto the device. Those static certificates typically rely on hardware security to mitigate certificate-based attack vectors. Onboarding and provisioning is challenging, particularly at IoT scale. I think anybody that's tried to do in-house PKI in a traditional enterprise is very aware of that, where maybe a large enterprise would be considered 20, 30, maybe 40,000 devices. And certainly Device Authority and Symantec with their managed PKI and IoT Roots of Trust program are very used to delivering and deploying these into environments that might consist of hundreds of thousands, if not millions of devices. And then fundamentally, sitting above that in terms of the security of data, TLS, as I've already mentioned, or transport-based approaches do not provide end-to-end protection for data, or it's certainly very challenging to do so, given the complex journeys that a lot of data, IoT data, takes. So in terms of device authority, we're providing this strong trust anchor that's bound to the DNA of the IoT hardware itself, to both help provision existing certificates and protect those. We're also using that dynamic certificate for either one-time use keys or for the encryption of static certificates provisioned out of the Symantec managed PKI. That dynamic architecture is all secure and policy-based, providing automation around PKI. And finally, we're delivering using the same dynamic key technology, a data-centric approach to encryption, rather than relying on or layering on top of existing transport-based provisions. So delivering real true end-to-end security for those payloads. And really to sort of finish off in terms of how that hangs together and our relationship with Symantec and the work that we've done with those guys. If we take this relatively straightforward architecture diagram, we really have three elements. We have the Symantec managed PKI in the top left-hand corner. We have our back-end, or the device authority back-end component, which is running either in a physical data center or in a cloud. And that's really delivering a lot of the integration with the Symantec managed PKI. And then we have on the bottom right-hand side the IoT device, which may be an IoT endpoint or indeed an IoT gateway containing our software stack. So just to take one example, because there's obviously a whole bunch of scenarios here that we haven't got time really to go into, but to take the fairly typical example of the basic certificate provisioning process within the integration that we've achieved with Symantec, and what you would typically see is an IoT device sending a certificate provisioning request out to our back end. That would be followed with a secure provisioning challenge sent from our back end back to our authentication engine running on the IoT device. That secure response is delivered back to our security engine at the back end, and then basically on behalf of the IoT device we make the certificate request into the Symantec managed PKI, which is then delivered to us and finally securely delivered to the IoT device endpoint in an encrypted state for decryption and then storage optionally in the TPM or the secure element of the hardware if that exists. If it doesn't, obviously we can persist the encryption around that certificate as required, and then dynamically decrypt that for use in the event that that's required for whatever purpose. So in summary, before we go on to questions in the last 10 minutes or so, we're simplifying security of the Internet of Things by delivering this strong trust anchor using patented dynamic keys. We're providing policy-driven data-centric encryption for all IoT data moving across those end-to-end ecosystems. We're providing trusted authentication services for not just devices, but also service layers, APIs and applications. And that's all in a standards-based solution that doesn't disrupt existing data flows or applications, which is pretty key for brownfield or legacy implementations of IoT. Brian mentioned this and referenced this a number of times. Security first is really an essential paradigm, we believe, for IoT moving forwards, and we're really empowering that by delivering stronger security posture for industry IoT leaders like ThingWorx and Symantec. Thank you very much for listening. I think we're going to move across to questions. I think we have a few that have been posted over the last 45 minutes or so. So I'll hand back to Rosa to run through the questions that we're able to answer in this session.
Thanks, John, and thank you, Brian, as well. So I have had a few questions come through. I'm going to come over to you, Brian, first. Whilst you were presenting, a question came through asking, is ECC secure enough? So
I think there has been good work done to date on cryptographic key strength of elliptic curve relative to RSA. and I think it's broadly accepted by both a variety of national security communities as well as financial services communities and others that literally bet trillions of dollars on crypto. That elliptic curve asymmetric key, the strength of elliptic curve relative to RSA is very good and very strong. Now there is an open question. If we get out our crystal balls and wonder, when quantum computing is going to have the power to break the leading asymmetric key algorithms that are out there right now. Both RSA and elliptic curve are susceptible to quantum computing when there are quantum computers that really scale. And if anybody wants a quantum discussion on qubits and quantum bits and physical quantum bits versus logical quantum bits and where quantum computing is today, happy to have that discussion in an offline. But a lot of people put a consensus estimate around 15 years, that it might be 15 years. Some say sooner, some say longer, before quantum computing will break elliptic curve and RSA. And for that reason, we're encouraging people to do a lot of the asymmetric ciphers in software as opposed to necessarily baking them into hardware, or at least leave enough headroom to maybe swap in a different asymmetric algorithm if your device is going to be in the field for more than a decade or certainly more than 15 years. And so those are some of the things that I think are important to consider for devices that are going to be in the field for a long time, have that update capability to swap in a different asymmetric cipher eventually. The quantum resistant ciphers that are under evaluation right now, I personally don't believe they've been subjected to the same rigor as, say, AES, the Advanced Encryption Standard for Symmetric Crypto, or elliptic curve, or RSA. On elliptic curve, also, you want to be careful with which curve you're picking. There are concerns with specific curves, so you want to be smart on that. But overall, net, I do believe that elliptic curve, in the right key length is just as strong or stronger than RSA. So the common example that's given is elliptic curve 256 being as strong as or stronger than RSA with a 2048-bit key length.
Okay, thanks, Brian. Now a question for John. John, on devices lacking secure hardware elements, how can device authority prevent keys from being used on devices different from the device on which the key was created?
Yeah, thanks for that question. It's a very good question. I think you'd have seen me reference in a number of the slides the dynamic key capability that we have on device, and this is really central to our ability to protect local assets on those devices, but also importantly tie those assets back to that device and that device only. And that's really because the dynamic key generation is effectively constructed from the hardware, or using entropy from the hardware of that device and that device specifically. So any attempt to effectively utilize that same key on another device basically wouldn't effectively work, because there wouldn't, in essence, be a match from the device that was the key was originally created on. So we're actually using that to actually create a symmetric key to allow us to secure the certificate on the device. And because that symmetric key is bound and can be dynamically recreated, but only dynamically recreated on that device, you in essence have partitioned that certificate to only effectively work or be able to be decrypted on that device specifically. So hopefully that goes some way to answer the question that was asked there. I think there was a question about demonstrations. Certainly, what we're planning on doing is creating a demonstration, a recorded demonstration asset to support the presentations today, and we'll hopefully be rolling that out over the coming weeks, and certainly the attendees from this event will be getting a notification as to when that's available.
Okay, thanks, John. Any questions we've not been able to answer will be answered individually later this week. I'd just like to say a big thank you to our speakers, Brian and John, and I'd also like to thank everyone for their time and interest, and we look forward to speaking to you further in the near future.